Hi, my name is Emma Deegan, and this presentation is about understanding aberrations. So we are going to explain how aberrations work, what they are, go through all of the names, how they affect vision, and also the practical applications that you might find in practice. So clinical applications, mainly we think about wavefront technology with refractive laser surgery. Some of the modern laser systems can offer a wavefront treatment and have been doing so for the last 25 years. So LASIK or LASIK patients may be offered a wavefront treatment when they go for consultation. Also, the wavefront systems have allowed us to use topography-guided treatments, where instead of creating a treatment based on the wavefront, we actually base it on the topography. This is used to fix distorted corneas, so in keratoconus or decentered ablations. Modern IOLs also correct aberrations, so we will talk about spherical aberrations which they correct. And also they help us understand real-world vision. So the patient who, although they can see all the way down the chart, still isn't happy with their vision, sometimes looking at how the aberrations are affecting their vision helps them describe it. So wavefront treatments are really just an advanced treatment profile tailored to your patient's specific requirements. It uses advanced optics to measure and treat real-world vision. And also there is a reduced risk of glare and halos and port night vision associated with wavefront treatments. So what are aberrations? First of all, I'd like us to do a little exercise. So if you get a pencil and paper, cover your left eye and then turn out the lights. And now if you look at this black screen, there's a red dot in the center. You can do this with any red dot, like a little LED light or something. And whilst covering your left eye, draw your right eye. With your right hand, you can draw the shape that little dot is. If you look at it, initially it just looks like a red dot. But as you look closer, you see that there's like little ghosting images around the outside. So if you draw what you can see, and this is what we call your point spread function. So this is a very quick way to work out if somebody has got a lot of aberrations or not. It's very basic though, so it is just an approximation. Okay, so what a point spread function is, it's a representation of an image like a distant star, how it makes on your retina. Every point of light is going to create this shape, and that will be distributed across the retina. So for instance, if you have a point spread function that is just a single dot, your amount of aberrations in your eye will be negligible. Or if it looks like a big Mercedes-Benz symbol, then you have a lot of aberrations. Point spread function will vary with pupil size, so it's interesting to look at your point spread function in daylight. Our exercise, we do it at night because in night conditions, because that's when you'll see the most aberrations. And it's also a useful way to describe vision. So for your patients, if we look here, if this was your patient at 2 millimeters, they can have quite a point image, so not too much distortion. However, when the pupil dilates up to 7 millimeters or 6 millimeters, you can see that dot becomes distorted, and it's going to give a few interesting descriptions of their vision. Zernicke polynomials are really the way that we describe these aberrations. They're a mathematical term and seen as very complicated. I'd like to simplify it so that you can understand it really from first principles. So what we're going to do is we're going to look at this shape. Okay, so to give that shape a name is quite difficult. However, if we say that it's part of a circle, part of a square, part of a triangle, we can now record that measurement, and if we record the location, we have described that shape quite simply. This is how the Zernicke polynomials work. They are basically shapes used to describe a wavefront, and normally they're presented in this pyramid shape. So if we start at the top of the pyramid, the zero order is piston. Okay, so if you imagine an object coming closer or moving further away from you, it will get larger or smaller. Okay, and that's what piston is. It's describing the position of the optic in space. Okay, and it is right at the top of the pile. 0 is piston. Tilt is the first order aberration, and this relates to when we look at straight lines, we assume here that the columns are straight at 90 degrees to the bottom of the building. However, because of visual anomalies like parallax and things like that, we find that actually that column isn't straight, but we perceive it as straight. Okay, that's what tilt is. Tilt is how much an image is tilted where we're looking at it. And that is the second order. Okay, the first order tilt. So really, orders 1 or 2 really don't describe the vision. They're all about where your object is in space and putting it in a position so that we can then describe it. So normally we ignore piston and tilt, but the reason I've explained them is in the 25 years that I've worked with aberrations, nobody has explained 0 or 1 order aberrations to me. Everyone just says, oh, we don't use them, so don't worry about them. So I just thought I'd let you know what they are. There really is nothing to do with them exciting, but at least you now know what 0 and first order aberrations are. So we're going to ignore the first 2 lines of our pyramid. That takes us to the third level, which is called second order and contains the terms defocus and astigmatism. This is the sphere and the cylinder. So one thing to note is that according to the ANSI standard, which is what we're all governed by, cylinder terms are given 2 values, horizontal and vertical. And if you think back to college when you learnt about combining cylinders using a Stokes construction, here you can see that you've got a cylinder on the y-axis with an amount and an x-axis with an amount. Or you can do like we do in refraction, is we give a vector at an angle, so an amount and an angle. For aberrations, the ANSI term is 2 terms, horizontal and vertical, but you may see sometimes them compressed to give 1 value. Okay, so I hope that that's clear, but that's why on the pyramid with the second order, we see that we've got defocus in the middle and astigmatism either side. Okay, so here we can see the spherical wavefront, and then we've got the cylinder in horizontal and vertical. So third order aberrations, and this is really what we start to consider as high order aberrations. Trefoil and coma are the main parts, and these are quite important, have quite an important act on your vision. Coma looks like a hill and a valley, and trefoil looks like a 3-cornered hat. On the pyramid, they are here, the third order, these 4 terms. So we have horizontal coma or vertical coma, and there is a low point and a high point on the wavefront. Okay, so this is commonly seen in decentered ablations where the ablation hasn't been put on the centre of the cornea, so it's actually removed some tissue that it shouldn't have done, and it leaves behind this kind of hill and valley formation. Okay, the point spread function, if we think about it, for a coma is going to be like a streak, and then trefoil, which is the outer terms, looks like a 3-cornered hat or a Mercedes-Benz symbol. So on your patient, they may have some vertical coma and some horizontal coma, and that would look like this. So here, if you look at the side of this tail light, there's a streak coming out of here at about 135 degrees. So that would be a coma term containing both horizontal and vertical. So you can see here how useful point spread function is for someone describing their vision. They might have a bit of a streak, there might be a bit of a Mercedes symbol in there, and all of these terms will be given values which express how much of each term they have. Fourth order, which is the 5th line down, is where the aberrations start to get a little bit more complex in shape. Spherical aberration, which is in the centre, here. This is the one that really affects our vision at night. It doesn't change it during the day, but at night it generally becomes more myopic. This means, like for me, I was -2 in the center of my pupil during the day, but at night I was about -3. So my night driving was pretty horrific until I had my wavefront treatment, which corrected all of that. Okay, the outer terms are the secondary astigmatism. So these are related to the astigmatism, just more complex. Okay, and then here on the outside we have quadrifoil, which is a little bit like here the tetrafoil, but again just getting more complex. So you see, as the terms go down, they get more complicated. The easiest way to understand them is to look at the effect it makes on point spread function. So if we're looking at spherical aberration, you see these kind of rings, a bit like an Aries disc or a spider web. This is our secondary astigmatism, which looks like a square or a diamond. And then we have the quadrifoil, which is like a four-peaked hat, if you like. So when you're looking at point spread functions, or even when you look at the one that you drew for yourself, you can see what sort of terms are in your point spread function. Fifth order and above, the aberrations just get more complex and really don't have much visual significance. So we normally say that 0.1 to 0.2 microns of wavefront is what somebody can just visually detect. So if your amount of aberration is 0.005, the patient's not going to be able to determine it. Okay, but we measure them anyway. So some machines will measure upwards of the sixth order, but really we are concerned with this third order aberration and fourth order when we're thinking about higher order aberrations, and low order aberrations we're thinking about this line here, the second order. So hopefully that has made that pyramid seem a bit more understandable. Okay, so third order aberrations and above, these are our high order aberrations. Okay, sphere and cyl we understand, and the higher order aberrations can't be corrected by sphere and cyl. So those are the ones that we need to understand. We've looked at the Zernike pyramid and we've decided that we don't need to know about the 0 and 1. The second order, which are shown on this little graph, are going to be sphere and cyl. So we're really only interested in the higher order aberrations. So what this animation does is it looks at the Zernike term. So Z440 is spherical aberration. And here, and then it looks at all the different point spread functions for those terms and gives us an idea of how distorted they would make a grid. As the aberrations get further down the pyramid, you'll see that the term gets much more complex. However, the amount of this term in the wavefront map is going to be negligible and the patient won't really determine them. So the terms that are important to us are ones beginning with a 3 and a 4. So this should start up again in a second once it's got through the seventh order. You can see how complicated these shapes are. Okay, so now we're going to start with the sphere and the cylinder. So cylinder has 2 terms, and now we'll go on to the third order. So 310 is coma, and then you've got your tetrafoil, and then we go into the fourth aberration, which is spherical aberration, etc. And you can see how distorted it makes it. Also, we can look at the effect of these higher order aberrations. So now we're just looking at the third, fourth and fifth aberration. And you see here on this patient, they have quite a big point spread function. If I remove the third order, that's the coma and the trefoil term, you can see it has an effect. If I remove the fourth order, and then these are just the fifth order aberrations, and then these would be other aberrations which aren't really detectable to the patient. So using point spread function is quite useful, and most systems will have a calculator where you can play about with them. Okay. Now we need to think about measuring the wavefront, and to do that we use RMS, which stands for root mean square. It's basically a calculation which takes the root of the mean of the square. It means that all the numbers are included and their signs are irrelevant. So a -1 has much of an impact as a +1. If you didn't do this, you would just end up with a flat wavefront, which hopefully I'll describe here. So here's our wavefront, here's our eye, and this is the plane wavefront, the perfect wavefront which we measure everything from. Some of the aberrations will be further away from the patient, and some of the aberrations will be closer to the patient. So if we add them all together, the ones further away and the ones closer to, you will end up with 0, a plane wavefront. Okay, so root mean square because it's going to square the numbers and then take the mean, and the square root is actually going to give us a number which takes into account the amplitude both ways. To simplify, RMS is a number with which we quantify the whole wavefront. As a pupil gets bigger, the RMS will increase. So always check the diameter of pupil that you're looking at. The ANSI standard is 6 millimeters for this. But sometimes, if you're looking at a cataract study, they might refer to a 4 millimeter pupil. This is that in IOL surgery, the pupils are a bit smaller and we're more interested in that more central 4 millimeter area. This is what a wavefront map will look like. So the cooler colours are further away and the warmer colours are closer to us. The cooler colours are positive and the warmer colours are negative. Okay, so this, if you had one like this looks like a bullet. This is a myopic wavefront. We can also look at them as a list. This is a report from the Pentacam. It only contains aberrations from the corneal surface, not the whole, but you can see here the number is of the aberration is listed, as is the order and the mode. So that gives you the position on the wavefront, and then down here it actually gives you the name so that you can have a look and see with the name. So if we look here at coma, and then it gives you a value for the amount of coma in this patient's eye. This here is the RMS for the wavefront, and then this line here says for this amount of coma, the black line is your patient and behind it is a normative graph. So this is saying that this patient's coma is normal, but it's at the higher end of normal. Okay, the trefoil, for instance, is in the first standard deviation away from normal on the lower side. Okay, by looking at aberrations like this, you can detect patterns. So in early keratoconus, they tend to develop vertical coma because that's obviously the way the cornea is shaping, and you would expect the bottom to be, in terms of topography, steeper than the top. This will have a knock-on effect on aberrations. And aberrations are very sensitive, so you sometimes can detect change using an aberrometer or looking at the Zernike terms for the cornea than you can by looking at a topography map. How the systems are devised. So there are many different optical principles for measuring aberrations, from using our pencil and a little red light to things like the Hartmann-Shack system. This is the most common and is sort of one of the earliest ways of detecting it. The optical principle I quite like because it's very simple and it is based on something we know very well. That is that the central ray is going to pass undeviated through the optical centre. So what you do is you have a grid with a camera, okay, and you have a little thing called a lens array. So that's just like a grid of lenses. And as the light wave go through from the eye, they will hit the lens array and one central ray will pass undeviated and that will create this perfect grid. But most of the time they're going to pass through a different part of the lens, so they are going to be deviated. So this is what a perfect wavefront would look like, And this is what an aberrated wavefront would look like. So the spots, instead of being right on the grid, are found in the box. Okay, so it's a very simple process, a simple camera, and then the software will just work out what aberrations are causing that distortion. However, one of the drawbacks is that sometimes you see that the spots don't stay in their grid. They're deviated so much that they sit in a different box. Then the software can't identify where these rays have come from. So it's either going to discount them or make an assumption. Either way, that is the main downside of the Hartmann-Shack system, is that in an aberrated eye, not all points are able to be detected. So clever people have come up with a pyramid wavefront center. What this does in essence is it uses a pyramid to split the light so that these more points can be detected. Very roughly, it's like when we went from time domain OCTs to spectral domain. We put, instead of analysing one light ray at a time, we put a box in that will let us analyse multiple rays. Okay, so that's really what the pyramid wavefront sensor, which you find in like some of the CSO aberrometers and the Schwinn sensors, the more modern sensors are using now. Another sensor is in the Nidec OPD scan, and this might be familiar because it's based on the principle of automated retinoscopy or dynamic skioscopy. This measures the aberrations and it will quantify them because it also has a topographer in terms of cornea, whole eye aberrations, and then it can split out the internal aberrations. This is particularly useful for cataract surgeons because once the lens is gone, you really want to know how much of an impact that lens was having on your aberrations. So you know about correcting or not inducing anything by taking the lens out. So this report, the Dyer report on the OPD scan, is very useful for looking at cataract patients. It gives you the cylinder, also gives you an idea of the total cylinder. It looks at the corneal sill and the internal cylinder. It will give you information on the pupils, the mesopic pupil versus the photopic pupil. This gives us an idea of where the patient's looking, or where the patient in the day and where they're looking at night. And if there's a big difference, is this going to cause a problem? And also it looks at the refraction in the centre of the pupil and at 3 millimeters. So again, what is the patient's refraction like when they're driving during the day and driving at night? This will also indicate if they have a lot of spherical aberration. So what is a wavefront treatment? Basically, you have to do some advanced diagnostics. You need an aberrometer and something to measure the corneal shape, like a high-end topographer or tomographer. You then need to be able to plan your treatment. So you have 3 types of treatment. You have a standard treatment, which is where you would just enter the sphere and the sill into the laser. You then have a wavefront guided treatment, which is where you would take the output of the aberrometry file, convert it using the treatment planning, and then fire that directly onto the cornea. And then you have topography guided treatments, where you work out a treatment based on the topography, and then you may go and do a wavefront treatment once that's all settled down. Okay. With standard treatments, some lasers will offer a wavefront treatment, but it's not based on the patient's aberrations, it's based on what the laser is going to induce. So it might be a wavefront corrective treatment, or there's all different terms. But essentially, if the treatment is just typed into the laser as a sphere and a sill, that is a standard treatment. If you are going to treat the wavefront, that is a wavefront treatment. And if you are going to smooth the cornea using topography, that is a topography guided treatment. Okay, and then you obviously need a nice laser to create a flap maybe, and then to deliver the treatment. Also, for IOL surgery, aberrations have become more important. And this is a study based from Professor Maeda's study, and he looked at creating this report which is used on the pentacam to screen patients for multifocals. In essence, you look at different areas, and if your patient falls within a certain criteria, they're suitable for wavefront and a multifocal lens. And if they have too much aberrations, then really the patient's optical system is too compromised to cope with the optical demands of a multifocal lens. So one of the things that Professor Maeda says is that if the high order aberrations here at 4 millimeters are greater than 0.3, it would be okay to do a patient with multifocal lenses, but with caution. If this figure is under 0.3, then that patient is suitable for multifocals. And if they are over 0.5 RMS at 4 millimeters, then they're not suitable for multifocals. So for information on Professor Maeda's study or any of the references from this presentation, please see my article in The Optician, which is also on my website. There are more details of other courses, or you can check my YouTube channel. Thank you very much.